Yes. Okay.
Okay, let's start our next talk. Our next speaker is Zhuoke from BIMSA. Please welcome.
So first, it's my honor to talk in this workshop to celebrate Professor Krylov Vice birthday, and also thank you for the organize this wonderful workshop. So my talk is about the new approach of the algebra voices. So it's based on my PhD thesis under the advisor Professor Scalendo at HSC Moscow. You can find all the results in the talk. First, let me start from finite type invariant, also called Bashaliyev invariant. So, for any knot invariant V, you can extend to the knot with a double point. Here, I say double point, which means a simple double point. Yeah, and those, also, so this I call it finite type invariant. So, yes, yes, yes. Yeah. So this knot invariant, it's called Bashaliyev invariant, finite type invariant. It's order at most n if its extension vanished on all the singularity nodes with more than n double point. And so it's related to the rhetoric object chord diagram. You get a circle and you get a separate chord. And you can get this chord diagram from a singularity node. You just go through the circle. And if you meet the singularity node, you just put that 2 point uh, point out and just draw a chord between these two vertices. No, no. So it's just a pairing or involution of two elements on circle. So there's no. I draw some like overlap here, of course, but this is not important. So there's no any logical structure here. So it's totally combinatorial. So it's a pairing or involution on two element. So this is like chord diagram. So, and so you can get this chord diagram from the singularity node by just to draw this singularity as a chord. So there is a Fortran relation for nodes because that's if you want to recover a knot invariant from the function on the singularity node, you have to satisfy this Fortran relation. And this relation could be easily proved by following the four equations. And this Fortran relation for nodes, you can rewrite it on the chord diagrams. Here I draw it called Fortran element with this following diagram. So get so I looking at the two chords, and you just move one of the endpoint of the one chord to the or place of another chord's endpoint, and all the other chords are related to the same. So each partially if not invariant of order n is determined a function on the chord diagram with n chord, and is vanished on no Fortran element. So this function I call it weight system. And according Punch Services 1993, every weight system arises from a certain partially invariant, which means that the partially invariant is kind of like equivalent to the weight system on the chord diagram. So it's determined if and only if. Huh? Yes, yes, yes. And then there's a bialgebra structure on the chord diagram. The product just cut one chord diagram anywhere, and cut another chord diagram anywhere, and just glue this two graph together. They get coproduct delta. The delta D is the summation of the dj tensor dj bar, and J is a subset of the chord. So I'm going to talk about this Lie algebra wave system. So there are a lot of ways to define a specific wave system on the chord diagram. Some simple one is defined by some graph invariant of the intersection graph. And another big family of the wave system, or Lie algebra wave system, is associated with the Lie algebra, and this construction is given by constructors. So G is Lie algebra, and there is lead invariant bilinear form. And we just choose base E1, E2, ED. D is dimension of G. The dual base E1 star, E2 star, ED star is a bilinear form. And given chord diagram D with n chord, we just for example, I took this example that's a chord diagram with 3 chords. We just cut it anywhere and draw it as like arc diagrams. And I just put this the element for each endpoint. For the red chord, I call it A. So at the first endpoint, I put the EIA, and the second endpoint as EIA star. So the wave system is defined by the summation of the product EIA, EIB, IC, IA star, IC star, IB star. Take the summation. It's called the Lie algebra wave system. And there is a theorem from the Bernard and their observers say that this evidence is not depend on the choice of the base point and not depend on the choice of the base of the Lie algebra. And this results is in their not just the universal enveloping algebra of G is the center of the universal enveloping algebra, and also it's satisfied Fortune relation. So it is really a wave system on chord diagram. And this construction is easy to see. That's how to construct it, but it's very hard to compute. And so there's only SL2 wave system is known before. So and also that's the quantum invariant can also produce from partial Liev invariant. So theta k is a quantum invariant, and it's a polynomial in Q and power -1, and we just let Q equal to e power h. This coefficient of this higher expansion is partial Liev invariant over there. And the colored Jones polynomial is related to SL2 wave system, which is a well-known wave system. Actually, home-fly polynomial is related to GLN wave system. So this Lie algebra wave system is quite powerful. So I'm going to talk about the GLN wave system. So the Lie algebra GLN, everyone knows it's n times n matrix. And I take this bilinear form is taking trace. And I choose the base EIJ. It's the elemental matrix has only one as the i's rows and j's columns. And the real base EIJ star is EJI. And this is a permutation relations. So I want to say that for this GLN wave system, it was known that under the standard permutation, that's wave system. But we don't know how to calculate it in the universal enveloping algebras. So next, I'm going to talk about some structure of the center of the universal enveloping algebra of GLN. We take the simplest chord diagram with one chord, and by the definition, it is the summation of EIJ EJI, and this is I call it the second Casimir element. And by this way, you can define that the lot of different Casimirs. C1 is the summation of EII, and CK is summation from EI1 I2, EI2 I3, EIK I1. So this is a Casimir element in the center of the universal enveloping algebra. And the center of the universal enveloping algebra of GLN is isomorphic to the ring of the polynomial. And the higher Casimir element, Cn plus, because you see this definition that you can define for every k, but actually the center of the universal enveloping of GLN is only a polynomial ring of n elements, and the higher Casimir element could express the polynomial in C1 to Cn. by this Romoff formula. So this is the structure of the center of the universal algebra of GRN. And let me show you that example. It's how to calculate the weight system in the universal algebra. This is a chord diagram. I call it K2. We get two chords, and these two chords are intersected. The weight system WGRN K2, by definition, is summation of the EIJ, EKL, EJI, ELK, just the base. And we just trying to figure out how to connect the formula to the Casimir element. First, you just sweep the middle two elements and apply the Lie bucket, and go on and go on. You finally get this polynomial C2 square plus C1 square minus NC2. So by the way, that if you look at some specific representation of the GRN, the result is easy to calculate. So WGRN, for example, the standard representation, the chord diagram D is actually known as the n power the C of D. The C of D is that you can consider a chord diagram as a ribbon diagram with exactly one single vertex. The circle is actually a big disk, and this chord is actually the ribbon. This CD is the component or boundary component. For this graph, the boundary component is so you get only one component, which is the CD of this chord diagram is 1. And you can easily from this polynomial to get this result by after the standard representation. I think C1 is IN, C2 is n times I. And you take a trace that's on the standard representation. The result is the power 1, and here we get the polynomial C2 squared plus C1 squared minus NC2. So my way to calculate this GN weight system is by generalizing it to the permutation. So for permutation sigma, permutated on m elements, so I define that the weight system of this permutation is EI1, EI sigma 1, EI2, EI sigma 2, and EIM, I sigma m. Uh, it is my results. It's so it's based on the suggestion from the Professor Yang. Yeah, I do the following work. So for any sigma, it's the WGN sigma is around the center of the universal enveloping algebra, and this invariant actually cyclic computation I'm going to give later. So you can easily see that this definition is okay. The definition of the digraph of permutation. The digraph of permutation sigma in the SM is get m vertex and m direct edge. As follows: this is a one in one out graph. You just draw this n element on the line, and the direct edge from I to j if and only if sigma I equal to j. So this is an example that you get a graph of this evolution. Map 1 to n plus 1, plus 1 to 1, 2 to n plus 2, n plus 2 to 2, and n to n to n to n. And so the definition of this weight system on permutation is the weight system of the chord diagram is just a specific example of this weight system permutation. If you consider that chord diagram is an evolution of this to an element. So also I define that the Casimir element CM is I2, I1, I2, I2, I3, IM minus 1, IM, EIM, I1. So it corresponds to the cyclic permutation, and you can see that the graph is So 1 to 2, 2 to 3, m minus 2 to m minus 1, m minus 1 to m, and finally m go back to 1. This is the digraph of Casimir element Cm response. For chord diagram, its chord is evolution without fixed point on the tuned element. This value is the same value of the wave system under permutations. And so this is the result about the, how to calculate this GLN wave system on permutation. First, we start with the empty graph. Value is equal to 1. And it's multiplicative of this product of this two permutation. Permutation is just destroying the permutated set. And we get the standard cyclic permutation is 1 to 2, 2 to 3, minus 1 to k, k to 1 is the generator, ck. And then we have this simple relation. It's just gets two neighbored vertex k and k plus 1. They just switch the two places of these two vertex, and there you get two permutation have the lower number of the permutated elements. And particularly if that's the sigma k plus 1 is k, then you get the c1 and n at the right. So by this theorem, that we can calculate that permutation, the basis on permutation by recurrency relation, because that you can always split that switch the place of two neighboring vertex, and the difference is the lower number of the permutations. So the row rank of the permutations. And you can always by switch to neighbor vertex to make a permutation as a product of the stand cyclic permutations. And there also this value of the permutation is it's represented as a polynomial n c1, c2, c3. And by this definition, it is universal. You can define without the n. You can let n is just a variable like c0. So now I'm showing the computation of the value of the WGL on the cyclic permutation 1, 3, 2. So you get permutation 1, 3, 2, and you just switch the two endpoints, this 2 and 3. So you get permutation 1, 2, 3. And by this relation, you get C1 times the 1 vertex and the minus n times 2 vertex, 1, 2. So, and you see that the 1, 2, 3 is actually the standard cyclic permutation, which is C3. So the value of this permutation is C3 plus C1 square minus NC. So this is how to calculate the wave system under n permutations. You can show that the results. Show some results by computer. That's K2, K3, K4, K5. It's actually the chord diagram with n chord that's intersecting each other. So it's very complicated because it's a polynomial infinitely variable. And also that's I'm going to show you that this wave system on the permutation is not the only the wave system under permutation. It's actually it's the wave system under let's say on the round diagrams and not this diagram, because you can always move that the rightist the leftist leg, and you just move it to the leftist, and by this recurrence relation nothing has been changed. So actually when I say I say permutation 1, 2, 3, it's not just mean that 1 to 2, 2 to 3, 3. 1 is actually the round graph, 1 to 2, 2 to 3. So this wave system is not defined on this kind of diagrams. It's actually defined on graph, the round graph, same as the chord diagram. And the next that this following idea you can define also by this superalgebra GLMN. So there's the standard definition of the wave system chord diagram. You can also associate it to Lie algebra and Lie superalgebra. So by this idea, you have GMN, you get super bucket xy minus 1 power over x with yx. Super trace is trace A minus the trace B. And I use this as a bilinear form. And take the base Eij, ij from 1 to n plus. This is the standard base of the Lie superalgebra. And get a computation relation like this. So also that's the structure of the center of the universal enveloping algebra. It's also known that Ck, the summation of the minus 1 power I2 bar plus I3 bar plus Ik bar. So you see it's a little bit different with the GL and K, that you get a sign at each term before the summation. So also that's the definition of the wave system. We only need to figure out how to deal with this sign function. So we can define this wave system WGLMN of the thing sigma, the minus 1 power of the sign function f sigma I1, I sigma 1, I2, I sigma 2, Ik, I sigma k. Next, f sigma is a sign function, polynomial in I1 bar, I2 bar, Ik bar. And actually, we have a rhetoric version of this sign function. You can say that for a standard cyclic permutation 1 to 2, 2 to 3, k minus 1, so k minus 1 to k, and k to 1, has a sign function I2 bar plus I3 bar to Ik bar. And the way to define this sign function is you get the two parts. One is the linear part, another is quadratic part. So basically, you get a port from left to right. You just put it in the P1, which is the linear part. You get direct edge from left to right. And for each vertex, you just draw this the incoming and outcoming a little bit separated. The incoming edge a little bit left, and outcoming edge a little bit right. That if you have a cosine, then you just put I bar times IB bar. So it gets edge A and edge B is cosine section somewhere. You just put it in the second part. So this gives us a nice definition of this GLMN wave system for permutation. And this permutation is actually so the second theorem says that WGRMN for the permutation, it's actually the same as the GL wave system. If we only let that the m minus n is the C0. And the case cosmic element is also the CK. So it's kind of like giving the same polynomial, the universal polynomial of their permutation. So also I want to show some that conjecture from the calculations. So what I do is like for each permutation that we can give a polynomial. And the way is you get a recursion relation, and you just let the cyclic permutation is the generator CK, and the product is puts that the permutated set disjoint unit. So you may interested, for example, that for G one two, the summation of GL, which means we just take that kind of a mean value or average value of this wave system of the sigma. The sigma is a permutation of m elements. Just take the average vector. This is the summation of the m from 0 to infinite. This is C of n. It's the coefficient is a polynomial of n. It's one. It's a infinite variable polynomial. That point is g. So C1, C2, so on. This mean value, and we may expect that this kind of mean value is like related to some L function, because this permutation here is actually a one vertex hypermap. It's a hyper ribbon or generalized ribbon graph. So, and if you define like this, it is here. It is the C1, C2 is not actually the good base. So we apply the Harris-Chandler isomorphism, because the universal of the GL and write it as a minus GLN plus the GLN plus OH. We just do the projection by GLN over H. U over H is the C of the E11, E22. Yeah, and then there you get this Harris-Chandler project. And actually, if you restrict this projection on the center of the universal enveloping algebra, so it's actually give isomorphism. Here is a polynomial of the C1, C2. Here is called shift symmetric. This E11. Yeah. So the shift symmetric polynomial. Shift is using the shift. Yes, yes. So gets the shift to the Newton power. In this case, that's the summation of the EII minus Q over N plus Q over N minus I over K minus Q over N minus I power K. EII, I from 1 to N. And by this, you can get the Schur function 1 plus SK over summation K of I, SK. And by this, you can finally get that this G is a linear combination of this kind of SK. Finally, the mean value G. It's the SM minus the Q of N plus M minus 1, 2, S M minus 2 plus A4 N plus M minus 1, 4, S M minus 4. This 1 plus summation. Okay. Okay. Minus Zhuoke over a minus. But it's but I mean this is the result that you find it from calculation. Let's see. That's the
Yeah.
uh-huh. External relation. Yes, yes, yes. Yes. No, no. So yes, I know that there's the excellent result for SL2 and for SL3. That's we only know like a part of it, but so so you can get like a Jacobi diagrams by defining like this. This is two chord diagrams. As you get a triple point, and for SL2, you can always solve this kind of structure. Two times this, the way system SL2. There's also a way system of SL2, SL2. And for the SL3, I mean, if you get this, you can almost like resolve the order structure of this Jacobi diagram. And for the SL3, that I only know a part of this, how to resolve the structure of this Jacobi diagrams, is that the SL3. So you kind of like you can resolve like this kind of structure as something related to this. There's a number there. Some other terms, but it is not enough to solve everything of this Jacobi diagrams. You can get the results of. So because for SL2 it is a one-value polynomial. The Casimir only C2, and for SL3 there is C2 and C3. The things is very complicated. Oh, uh-huh.
Okay, let's thank the speaker again.